Now we'll begin Chapter 3. Chapter 3 is titled Airplane Aerodynamics. Basically what this chapter is about, we're going to look into air and the properties of air. In particular, how that relates to pressure and density. Air pressure and air density are two very important things to understand for a pilot. So to begin, airplane aerodynamics. Air shares properties of a fluid. It flows, it changes shape. Air has mass and weight. And since it has mass and weight, it is a body. As a body, it reacts to scientific laws of bodies in the same manner as other gases. What's important to know here is that at sea level, air, the atmosphere has an average pressure of 14.7 pounds on each square inch of surface. Also measured as 22.92 inches of mercury. The higher in altitude you go, the less air there is. For that reason, the weight of the atmosphere at 18,000 feet in altitude is 1/2 of what it is at sea level. Now, knowing that principle allows the pilot to take consideration for how long it will take him to take off from a runway, stall speeds, speed required to maintain lift, things of that nature. Also, you have many instruments on an airplane that rely on that information to give you accurate indications. So in particular with air, we have air pressure. The atmospheric pressure. Atmospheric pressure it lifts your airplane. Let's see. I'm just going through my notes here. See what's going to be an important concept to point out to you. And under pressure, there is a discussion about pressure, mass, the attraction of gravity, and also some insight on scientific laws of fluid and air gaseous substances. So I'd encourage you to read that. I'm sure we will pull a test question out of that portion of the text. Let's move on to density. Density of air has significant effects on an airplane's capability. As air becomes less dense, in other words, as you increase altitude, it reduces power because the engine takes in less air. It reduces thrust because the propeller is less efficient in thin air. It reduces lift because thin air exerts less force on the airfoils or wings. So because density is so important, we're going to get a little bit more involved with density. We're going to talk about the effects of pressure on density, temperature on density, the effects of humidity on density, and then we'll look at Bernoulli's principle of pressure. The effects of pressure, since air is a gas, can be expanded or compressed. When air is compressed, a greater amount of air can occupy a given volume. When pressure of a given volume of air is decreased, air expands and occupies a greater space. The original column of air at a lower pressure contains smaller mass. That means the density is decreased. Density is directly proportional to pressure. If the pressure is doubled, the density is doubled. If the pressure is lowered, the density is likewise lowered. Something's important to remember about that statement is that it is true only at a constant temperature. The effect of increasing the temperature of a substance is to decrease its density. Or decreasing the temperature will increase density. Thus, the density of air varies inversely as the absolute temperature varies. The statement is true only at a constant pressure. In the atmosphere, both temperature and pressure decrease with altitude and have conflicting effects upon density. However, the fairly rapid drop in pressure as altitude is increased usually has the dominating effect. Therefore, density can be expected to decrease with altitude. I'd encourage you to read over that a couple times, and I'm sure you have a strong understanding of it. The effects of humidity on density. What we've talked about before, when we talked about the effects of temperature and the effects of pressure on density. Assume that the air is perfectly dry. However, in reality, it's never completely dry. A small amount of water vapor will always be suspended in all air in the atmosphere. Humidity can become an important factor in the performance of an airplane. Water vapor is lighter than air. Moist air is lighter than dry air. It is lighter, that means it's less dense. Pressure, temperature, and humidity have a great influence on airplane performance because of their effects upon density. Now, we'll go on to Daniel Bournouille, a Swiss mathematician, explained how the pressure of a moving fluid varies with its speed of motion. All right, so specifically, here's what he said. He stated an increase in the speed of movement or flow would cause a decrease in the fluid's pressure. That's exactly what happens to air passing over the curved top of an airplane wing. It's a very important concept for you to know. Air has viscosity and will encounter resistance to flow over a surface. We know that all things have some sort of a property of adhesion. Air does as well. So it will encounter resistance as it flows over a surface. That's known on its airplane wing as skin friction drag. As air passes over the wing surface, the air particles nearest the surface will come to rest. The next layer of particles is slowed down but not stopped. Some small distance from the surface, the air particles are moving at free stream velocity. The layer of air over the wing surface, which is slowed down or stopped by viscosity, is termed a boundary layer. Typical boundary layer thickness on an airplane wing range from small fractions of an inch near the leading edge of a wing over to the orders of 12 inches at the aft end of a wing, such as on a Boeing passenger jet. You'll want to become familiar with the two different types of boundary layer flow. That's laminar and turbulent. The laminar boundary layer is very smooth flow, while the turbulent layer contains swirls or eddies. There's more discussion on that. You want to make sure that you have a complete and clear understanding. Now, the next thing we want to talk about is something known as the Magnus effect. And I'll read straight from the text. No, the explanation of lift can best be explained by looking at a cylinder rotating in an airstream. The local velocity near the cylinder is composed of the airstream velocity and the cylinder's rotational velocity, which decreases with distance from the cylinder. On a cylinder which is rotating in such a way that the top surface area is rotating the same direction as the airflow, the local velocity at the surface is high on the top and low on the bottom. There is a figure in your text to help you to understand this point. The important thing to know is that the difference in that surface velocity accounts for a difference in pressure. Pressure being lower on the top than on the bottom. So that airplane wing has a lower pressure on the top than on the bottom. A high pressure on the bottom pushes it up towards a lower pressure. Lift. Very important concept in aviation. There's more in-depth explanation of that in your text. Airfoil design. So we discussed how an airplane wing sustains flight when an airplane is heavier than air. That is due to the wing and airfoil design of a wing causing high pressure on the bottom of the wing and low pressure on top of the wing, therefore creating the effect of lift. In your text, it goes through a in-depth discussion of the structure of a wing, that shape at different attitudes towards the wind, and what effect that has on the aircraft. That's a lot of reading, a lot of talking. I'd encourage you simply to get a grasp of that on your own. I don't think it's going to do a lot of help for me to explain to you on this video when information is all there on paper and can be more readily digested that way. You want to also pay attention to the momentum effects of airflow. Bernoulli's principle of pressure by itself does not explain the distribution of pressure over the upper surface of an airfoil. A discussion of the influence of momentum of the air as it flows in various curved paths near the airfoil needs to be looked into and presented. You'll find that in your text as well. So the bottom line is this: the air pressure on the upper surface of the airfoil is distributed so that the pressure is much greater on the leading edge than the surrounding atmospheric pressure, causing strong resistance to forward motion, but the air pressure is less than surrounding atmospheric pressure over a large portion of the top surface. So that fluid flow over the wing is the basis for flight. And an airplane is a product of the velocity of the airplane, attitude of the wing, you'll see in Figure 7 in your text, it gives a pretty good picture of what the text tries to explain to you when we talk about pressure distribution over an airfoil and different attitudes of approach to the atmosphere and that effect on your aircraft. Let me look through these notes, and I think we've touched on the highlights. Of course, any questions, please email me directly, and I'll answer them as soon as I'm able. Coming up next will be Chapter 4.